Okay, let's jump right into this explainer. We're going to demystify that seemingly magical force that literally brings our modern world to life: electricity. You flick a switch, bam, the room is flooded with light. You plug in a phone, and you're suddenly connected to the entire globe. But how does this invisible force actually work? We're going to break down the incredible science here and make the whole thing completely accessible. We'll be zooming all the way out from the microscopic atom straight up to the massive power grids. Here's our agenda. 1. What is electricity? 2. Static versus current. 3. Magnets, motion, and generators. 4. Powering your home. 5. Measuring the flow. And 6. Power, safety, and the future. Let's get into it.
All right, Section 1. What is electricity?
So, to really wrap our heads around electricity, we've got to look at the tiny building blocks of the universe. You can't grasp the macro power of a city grid without understanding the micro reality of a single atom. Everything is made of atoms, right? And right at the center of every atom is a nucleus, filled with positively charged particles called protons. Circling that nucleus, kind of like planets orbiting the sun, are these extremely tiny, negatively charged particles called electrons. Normally, an atom just wants to chill. It wants to stay perfectly balanced with equal positive and negative charges. But when we apply a little energy and push those negatively charged electrons out of their cozy orbit, well, that's when things get very interesting. Here's the crucial point. That movement of electrons hopping into neighboring atoms is exactly what creates an electric current. Think of it like a microscopic relay race. When an electron gets forced out of its home atom, it shoves an electron out of the next atom, which shoves the next one, creating this steady stream of moving energy. And that flow? That is electricity. Moving on to Section 2, static versus current. Now, electricity generally takes on one of two forms, depending on whether it's just hanging out or actively moving. When you rub a balloon on your hair, you're physically scraping electrons off your hair and onto that balloon. The balloon builds up a negative charge, your hair gets a positive charge, and since opposites attract, your hair literally reaches out for the balloon. That is static electricity. It's gathered potential energy. Current electricity, on the flip side, is kinetic. It's that continuous, controlled flow of electrons we use to run our TVs, charge our laptops, and light up our homes. But hey, static electricity isn't just about laundry cleaning or party balloons. When massive amounts of static build up in storm clouds, where ice crystals and water droplets rub together to separate those positive and negative charges, it can leap to Earth as a lightning bolt. And get this, that sudden discharge of static electricity carries an unbelievable 300 million volts. To put that into perspective, a standard wall outlet in your house is only dealing with about 120 volts. So yeah, lightning is absolutely wild. We've been fascinated by this force for thousands of years. From the ancient Greeks studying static shocks way back in 600 BCE, to Benjamin Franklin proving lightning was just a massive electrical discharge in 1752. But the real game changer? That hit in 1831. When a British scientist, Michael Faraday, figured out how to actually generate this power on demand. Which brings us to Section 3, magnets, motion, and generators. So how exactly did Faraday and the modern scientists who followed him figure out how to generate this flowing power? It wasn't magic, for sure. It was a brilliant application of physics that we still rely on today for almost all of our power. The formula is simply magnets plus copper wire plus spinning motion equals an electric current. Whether you're burning coal to make steam or using wind to spin a propeller, the fundamental goal is literally exactly the same. You just need to create spinning motion around magnets and copper wire. Through a process called electromagnetism, spinning a turbine forces those electrons to move. See, copper is a fantastic conductor because its electrons aren't tightly bound to their atoms. So when a changing magnetic field spins near that copper wire, it physically pushes those loose electrons. They start banging into each other, passing electrical energy down the line like a giant high-speed game of pass the parcel. The electrons themselves don't travel instantly from the power plant to your house, but the energy they transfer absolutely does. Okay, Section 4, powering your home. All right, so we've generated this electricity at some massive power plant using turbines and magnets, but how does it safely reach your microwave? Well, enter the power grid. This incredible interconnected system makes sure power travels from remote turbines straight into our neighborhoods. It is, no joke, one of the most complex machines humans have ever built.
It grabs the electricity from the plant and shoots it across huge distances through those giant metal pylons and thick transmission wires you always see out on the highway.
But right before it gets into your house, transformers in local substations have to drastically step down the voltage. The electricity on the main grid is just way too powerful for your household wiring. Once the substation lowers that pressure, the power flows into your home's meter, goes through your breaker box, and enters a closed loop of wire called a circuit. When you plug a device into an outlet and turn it on, you're closing that loop, letting the electrons flow through the device, power it up, and continue on their merry way.
Section 5. Measuring the flow.
Now, if you check out the back of pretty much any appliance in your house, you'll see a sticker covered in numbers and symbols. To really understand our gear, we've got to decode this stuff. And honestly, thinking of a circuit like a plumbing system makes this incredibly easy. Volts represent the electrical force, exactly like water pressure pushing through a pipe. Amps measure the actual volume of electrons flowing past a certain point, kind of like the amount of water moving through that pipe. Ohms, they measure resistance. Think of this as a constriction or a narrow point in the pipe that makes it harder for the water to flow. And finally, watts. That's your total electrical power, which you get by simply multiplying the pressure, the volts, by the flow, the amps. This plumbing analogy perfectly explains why it takes so much more energy to run a heavy washing machine compared to safely trickling a charge into your cell phone. A washing machine might draw up to 1,400 watts of total power. It needs a massive flow of amps to literally spin a heavy, wet drum of clothes. Your phone charger? It only needs a tiny fraction of that, maybe 10 watts, because it's just gently pushing a small amount of electrons into a tiny battery.
And finally, Section 6. Power, safety, and the future.
As we look at the whole shebang, it's absolutely crucial to respect how powerful this utility can be while also looking at how it's shaping our future. Because our bodies conduct electricity, we wrap our cords in plastic. Plastic is what we call an insulator. Unlike copper, the atoms in plastic hold on to their electrons incredibly tightly. They offer massive electrical resistance, stopping electron flow dead in its tracks. That's why you can safely grab a power cord while it's plugged in. But if that plastic is frayed or if water gets in there, and remember, water is a fantastic conductor, it bridges the gap and you could receive a deadly shock. Always treat electricity with extreme caution. Today, we're rapidly changing how we actually spin those generator turbines. For over a century, we basically just burned fossil fuels to make steam. But we're innovating. Renewable wind power already supplied about 10% of all U.S. electricity back in 2022. By using wind to turn the turbines or solar cells to convert sunlight directly into electron flow, we're finding brilliant new ways to generate our most essential resource without pumping out harmful greenhouse gases.
Which leaves us with a massive, fascinating challenge. As fossil fuels dwindle, how will we continue to master the microscopic electron to safely and cleanly power our limitless macroscopic future? I mean, our entire modern civilization rests entirely on the backs of these tiny hopping particles. From ancient Greece rubbing amber to today's giant offshore wind farms, our grasp of electricity just keeps evolving. How we choose to generate it next is going to define the entire next century. Thanks so much for exploring this with us today on The Explainer. Keep asking those big questions, and we'll catch you next time.